Hello, welcome to the Wastewater Nutrients Process Control Testing Series. Today we'll be talking about ammonia. My name is Nicholas Willis, Senior Program Manager with the Environmental Finance Center at Wichita State University. A brief agenda for this training is it's going to be in three parts. First, we're going to answer the question, why are we testing for ammonia at our wastewater treatment facilities? Then we'll be looking at where to test for ammonia, and then finally, how to test for ammonia at your treatment facilities. So why do you test for ammonia? The main reason is that ammonia is toxic to aquatic organisms. Throughout the United States, many wastewater treatment facilities, especially those that are discharging to smaller creeks and rivers, have received lower ammonia limits in recent years as their permits have renewed. And that has to do with toxicity to aquatic organisms. Ammonia is in most wastewater permits. There are some out there that do not have ammonia limits, but most municipal wastewater permits do have ammonia limits in them. And one of the reasons for this is that wastewater, especially untreated wastewater, tends to be very high in ammonia because most of the nitrogen from humans reaches the plant as ammonia. So you have a pretty highly toxic wastewater entering the plant when it is viewed from an aquatic organism perspective. Another thing about testing for ammonia is that you can use it as a proxy. So if you have good ammonia removal at your plant, it's a relatively good indicator that either biochemical oxygen demand or chemical oxygen demand, depending on your permit, is likely being removed. Ammonia is a much faster and cheaper test to do. So for process control purposes, you can often use ammonia safely as a proxy for BOD or COD at your plant. Another reason you want to test for ammonia is that it is in competition with nitrate removal at many plants. So depending on your plant layout, there's a little bit of give and take between ammonia and total nitrate removal. So optimizing your process and making changes typically requires close observation. So the main competition with ammonia, between ammonia removal and nitrate removal, has to do with both space and time within your treatment facility. So ammonia removal requires an oxygen-rich environment. That's why you have blowers and aerators or surface aerators going at your facility to provide oxygen to the nitrifying bacteria in the water. Nitrate removal kind of requires the reverse of that. Nitrate removal takes place, the denitrifiers function to remove nitrate in oxygen poor environments. So if you run a treatment plant really oxygen rich, you'll typically have very, very good ammonia removal. Oftentimes we will see non-detect levels. But you're going to have, in many cases, quite high nitrogen levels, unless you have another step somewhere in your process to remove those, to have that denitrification going on. So if you are using the same basin to remove both ammonia and nitrate, testing for ammonia is a very good idea on a regular basis. So when we're looking at where to test for ammonia, for most plants, and there's a plethora of plants out there, so I may have skipped yours, but for most plants, you want to test at the overflow of your aerobic basin or the exit of the trickling filter. So it's typically the lower elevation coming out of your trickling filter. If you have parallel treatment basins, you probably want to test each basin because just because water is flowing through them in equal amounts doesn't mean the same thing is happening within them. Ammonia as a process control can help identify if one basin is working better than the other, and then you can help diagnose what's going on there. So for some plants, you may also want to test internal return flows. If you have industry in your collection system, you may also want to test some industrial dischargers at the sampling points you have set up for them. It's special cases, this whole presentation series is a series of generalizations. So there may be some cases where it's important to test for ammonia. So you might be a facility where you have batch discharge requirements. So you only discharge periodically. Testing for ammonia, especially if it's in your permit limit, is a good way to stay in compliance. Make sure that it's below the levels allowed. You may also test for influent if it seems like there's excessive loading or spikes somewhere else in your system. Ammonia can also be a good indicator of toxicity that has occurred to your plant's biomass population. So if something toxic has come in through the collection system, poor ammonia removal or a complete lack of ammonia removal is a good indicator that something toxic may be in your system. Occasionally, you might also want to monitor dewatering and decanting of biosolids, so the flows that are coming off that, especially if you're not doing this on a regular basis. So if you only deal with biosolids on a very irregular basis every few months or so, or seasonally, understanding the ammonia with internal flows can be pretty important because it can be quite high sometimes, depending on how the biosolids have been treated and processed to the point that you're decanting or dewatering them. So how do you test for ammonia at your treatment facility? The cheapest, fastest way is going to be a test strip. These are available from several different vendors. They tend to be pretty cheap, around $1 per test. And they're very suitable for daily process monitoring. So at the locations I talked about earlier in this presentation. There's also color wheels that function very similar manner to test strips. And they're a little more expensive, probably a little more accuracy to them. But really where most plants should be going, especially if they have gotten lower ammonia levels in their permits, is probably a digital colorimeter or spectrophotometer. So these have typically a packet or a vial, and you add wastewater to it in a certain amount, give it some reaction time, and then you put it in and there's a digital readout from it. These tend to be much more accurate than test strips or color wheels. You also have the issue that a not insignificant portion of the population does have some color blindness issues, and both test strips and color wheels can have some difficulties with people who are colorblind. So having that digital readout can help prevent that issue. If you have those stringent limits, a digital colorimeter or a spectrophotometer is probably the way to go, just because you have less error, it's more accurate. Many of these units also have some sort of a connection to a computer, so you can easily download the data off of it. That eliminates certain points of error in your recording and putting into a spreadsheet or something along those lines. It also typically is easier to dilute if you need to, because you're doing it in a laboratory setting instead of out in the field. I'll now be going through where to sample for ammonia at various treatment plants I've been to in my career. You'll be seeing aerial photos. All of these are from Google Earth, and then the labels are mine. So the first one is a SBR plant, so a sequencing batch reactor. This illustration here shows this is a 2-cell sequencing batch reactor. It does have a treated water equalization basin before UV disinfection. In normal operation, it would be a good idea for this plant to, test that water in the equalization basin or at the UV lights, kind of whatever is easier for access. Now, if they were having troubles with the plant, they may look at each basin. So perhaps there's been some toxicity enter the system, but in the SBR, it may have only gotten into one of the basins. So for some purposes, that's actually a good thing, because you have one basin that is probably fine. So looking at the decant from each basin would be a good place there. You might again also look at the EQ basin or UV lights, kind of record a profile throughout the plant. Looking at that influent, depending on what type of dischargers you have in your collection system, may be wise to do as well. Likewise, perhaps biosolids processing has overloaded the plant with ammonia, or you are decanting from sludge storage, might be a high source of ammonia. So lots of options there, but knowing your plant is a good idea, and having plans for where you would sample in cases of upsets or issues arising is also good. Good thing with ammonia, the tests are typically relatively inexpensive, so it's a lot cheaper to figure out the problem, spend a little more money on process control tests than to have permit violations or downstream fish kills or something along those lines. Next, we're going to look at kind of your basic oxidation ditch, extended aeration type of system. This is a small plant in Buhler, Kansas. Under normal operation, you'd typically be looking at the control structure before the final clarifiers, or somewhere in the UV disinfection area. The ammonia levels should be more or less the same. For troubleshooting, you'd be looking at that sludge decant and belt press return flows. This one does have a dewatering device, and then at the plant influent. So a little more simple than the SBR basin, just because there's less kind of treatment facilities in a plant like this. We're now going to move to a parallel plant. So the Ellenwood SBR was an example of a parallel plant in that each basin operated more or less independently. But many facilities do have basically parallel treatment facilities. So if you're going to be sampling for ammonia there, what would you do? So this is Edgerton, Kansas. They have a Schreiber system. So the first thing you want to ask yourself if you have a plant setup like this is whether or not the plants are truly parallel, or if they are sharing or mixing return activated sludge. I've seen it both ways, but understanding the internal flow dynamics is important to devising your testing strategy here. For routine sampling, if your basins are more or less equivalent, so they're sharing return activated sludge flows, they're getting the control structures to each basin are providing the same amount of flow, then you're going to want to sample at the UV and make the assumption that each basin is working more or less the same. But if you know the basins are not equivalent for whatever reason, you're going to want to try to sample that water after each final clarifier if you can. Now, your internal plumbing can complicate this matter, or it might be pretty easy. So you might have to do with a less than ideal sampling point sometimes. So maybe you'd have to pull off the top of the clarifier. That would probably work if you didn't have a better point to sample. For troubleshooting, again, we're going to go to that sludge decant and belt press return flows, and the influent are going to be our first places to sample if we're having ammonia troubles at the plant. Now we're going to move to kind of a classic biological nutrient removal plant with both anaerobic and anoxic zones that are built in. So this plant is meant to remove both nitrate and total phosphorus in a biological manner. It's located in Wellington, Kansas. So for routine sampling, just like every other plant, so coming out of the aeration area, so labeled here as treatment basin, is the weir to clarifiers. So when you're sampling this, the mixed liquor, you do want to be sure to let settling occur, and you want to take the clear water off the top and then sample that for ammonia. For troubleshooting, just like the other plants, you're going to be looking at sludge decant and belt return press flows and perhaps the influent. So what about a plant that has final both primary and final clarifiers? So this is a more traditional activated sludge treatment. It's a little bit larger. This is in Kansas City, Kansas. They're plant number 20. Similar to everything else, you want to be sampling that ammonia coming off your aeration basins. So in this case, it's a weir before the final clarifiers. I believe in this diagram, it's located as a splitter box prior to the final clarifiers. So you take the water off that, let the sludge settle out, and take ammonia off of the top clear part of the water. For troubleshooting, similarly, you're going to be looking at your sludge decant and belt press return flows and the influent in most cases. So I would like to highlight that to better understand how your plant is operating over time, it's important to keep good records. And this is a small treatment facility a little bit north of Wichita, Kansas, the city of Sedgwick. They have an oxidation ditch very similar to the diagram shown from Buhler, Kansas. And they are keeping a record of daily activities at the plant and daily measurements. So this is an example of what you may want to work towards at your own facility. They're taking readings from plant sensors they have deployed in various locations. So that includes dissolved oxygen, oxidation reduction potential, and online ammonia sensors. So this is a very data-oriented facility, and they do an excellent job keeping track of it. They're also tracking things, either on a daily or weekly basis, and they're also recording other tasks and measurements. Basically, they end up creating a plant log, all the way from very obvious things such as plant flow rates to the levels in the various basins, to the settings of various valves that control the flow both into, out of, and within the plant itself. And then they're recording the various process measurements that they take over time. And this will help them troubleshoot and understand, well, if I set this valve at a certain level, I start to have problems, maybe with ammonia, but maybe with something else related to treatment or permit compliance at their plant. There's also some other ammonia-related testing that may come in value at some point. So the ammonia removal process consumes alkalinity. And if you have water where the alkalinity is low coming into the plant, you may run into ammonia removal problems. So you may have enough air into your basin, but not enough alkalinity. And in that case, you're probably going to be adding alkalinity. So being able to test for alkalinity may be important, particularly if you're in an area with softer water or have really high incoming ammonia in your plant influent. Ammonia removal, somewhat related to alkalinity, is pH. The optimum removal is typically between about 6.7 and 8. So most plants have the capability to test for pH. If you're outside of this range, more likely than not on the low side, you may have ammonia removal problems. Dissolved oxygen, as we discussed, the nitrification occurs in oxygen-rich environments. So many plants have excessive oxygen, which wastes both money and energy and makes the nitrate removal difficult. So having a dissolved oxygen measurement, online sensor that you get information all the time is kind of ideal. Otherwise, there's handheld models of dissolved oxygen. Typically, if you're above anything of 2.0 milligrams per liter dissolved oxygen or more, you're wasting your energy. And you may be acting counter to your goals for nitrate removal. Oxidation reduction potential is another way to measure if the environment is conducive to ammonia conversion to nitrate. It's frankly more useful in the biological phosphorus removal, and we'll discuss it in that series a little more. Finally, your mixed liquor suspended solids concentration is important to keep track of. You need to have that adequate biology for ammonia conversion to nitrate. So if your MLSS is too thin, you may have every other set point right for your plant, but there's just not enough biology to convert that incoming ammonia into nitrate. If you are having some nutrient removal issues at your plant and you treat on average less than 1 million gallon per day, and that's the average, not the design flow, feel free to reach out to me. I have some capacity to help you out. I would probably the best way to contact me is via email, or here is my direct phone line as well. I hope this has been useful to you. Feel free to look at the other sessions on nutrient process control testing, where we will be covering nitrates and phosphorus. Thank you.